Okay, again, the question is designed for the purpose of showing you the geometric meaning of the derivative at a number. We'll go over the questions one by one. Okay. We all know the graph of the function f of x equals x squared. Actually, I did something before the class. The graph of the function is a parabola. Is that parabola? Now look at the mouse cursor. Okay, the parabola is something like this. We'll work on the questions one by one. Okay. For question 1, we just look for a point when x coordinate is equal to 1. Now let's recall each value of the function determines a point. I told you before. In particular, the output for the input of 1. To answer question 1, we need to evaluate the function at 1. Okay. Okay. We'll do question 1 first. Okay. Evaluate the function at 1. The value of the function at 1, you compute 1 squared. So 1 squared is 1. In question 1, we are looking for the point on the graph when x coordinate is equal to 1, when x value is 1, right? So the point we are looking for is the point with x coordinate of 1 and y coordinate of 1. Right. I did not write the full sentence for the answer, but I'm trying to save space. By that we mean on the graph, on the parabola, you look at the parabola only. Okay, the point we are looking for is that point, the point with x coordinate of 1 and the y coordinate of 1. Okay. Now look at question 2. It's very similar. Okay, in question 2 we are looking for a point on the graph where x equals 2. So by that we mean we're looking for a point on the graph when x value is 2. So likewise, we evaluate the function at 2. To answer question 2, we evaluate the function at 2, right? So we have 2 squared. 2 squared is 4. So the point we are looking for in question 2 is the point with x coordinate of 2 and y coordinate of 4. Okay. For the people who joined the class late, now I'm doing part 2 on handout number 4. Handout number 4 is updated. Okay. The question is designed for the purpose of showing you the geometric meaning of the derivative. I told you the conclusion last time, but I haven't told you why. Part 2 is designed for that purpose. Now we move on to question 3. In question 3, we are looking for the slope of the secant line to the graph passing through the 2 points. Okay. In question 1, we found a point with x coordinate of 1 and y coordinate of 1. In question 2, we found a point with x coordinate of 2 and y coordinate of 4, right? Now in question 3, where you connect these 2 points, you have a secant line. Okay. Secant line is a line something like this. I will show the graph in here. Okay, now you look at the graph. In question 1, we found a point with x coordinate of 1, y coordinate of 1, so that point. I believe you can see the coordinates, right? And in question 2, we found a point with x coordinate of 2 and y coordinate of 4. We found that point. Okay. Connecting these 2 points, you connect the 2 points, you have a line. This line is called the secant line. The secant line. Okay. So that is the secant line we are talking about in question 3. Okay. But in question 3, we are looking for the slope of the secant line to the graph passing through the 2 points. Okay. Okay. You look at question 1, you have point 1, 1. You look at question 2, you have point 2, 4. Now I want you to recall a formula for computing the slope you learned in high school. You're probably in Math 11, in pre-calculus 11. Okay. I think you were taught some formula like rise over run, but In question 3, I'm going to use m to denote the slope I'm looking for. Okay. The slope is computed using. Can we call 1 the first point? Can we call the 2 for the second point? I know it doesn't matter which point is first, which point is second, but it's easier for me to communicate. Okay. The slope is computed using the y-coordinate of the second point minus the y-coordinate of the first point. The difference is on the numerator, so which is 4 minus 3, right? Sorry, 4 minus 1, I mean 4 minus 1. And then on denominator you have the x-coordinate of the second point minus x-coordinate of the first point, so which is 2 minus 1. By that we mean the slope is 3 in this particular case. The numerator is 3, the denominator is 1, right? 3 divided by 1, you have 3. Okay. If you want me to reveal some more details, I think the slope for a point, the slope of the line passing through 2 points. So now let's say x1, y1, and the second point is x2, y2. The slope of the line passing through these 2 points is computed using the formula. On the numerator you have the rise, so which is y2 minus y1, so that is rise, right? Rise over run. Run is x2 minus x1. So this part is the review of the formula, okay, for computing the slope of a line passing through 2 points. So in question 3, so we're done question 3. Okay. We are not only computing so those slopes, and so later on we are going to observe some change, some pattern. Okay, now look at question 4. The meaning of question 4 is in question 4 we are looking for the slope of the secant line to the graph passing through 2 points. One point is the same as the first point in question 3, the point with x-coordinate of 1, actually the point 1, 1. The second point is the point with x-coordinate of 1.1. Okay. I will show you the meaning this time. I hope I can zoom in enough to show you the meaning. Okay, I'm going to make a h, so 0.1. I don't know, I have 0.1 or not, so come on. It's something like this. You still have a 0.11 on the graph, but the second point, you make the second point very close to the first point. It may not be shown properly on the graph, but I was trying to make this h 0.1. I don't know, I can zoom in far enough to show you what's going on. But one of the point is the point with x-coordinate of 1 and y-coordinate of 1. You have one other point, okay? You have one other point with x-coordinate of 1.1, slightly to the right of 1. Okay. Yeah. Anyway, we could compute the number. Okay. Now let's look at the pattern. Okay. In question 4, the slope is computed using. So before we compute the slope, it's easier if we figure out the point. Okay. In question 4, that's my scratch paper. Okay. In question 4, one point is 1, 1. The second point is the point with the x-coordinate of 1.1. Anybody want to tell me the y-coordinate if x-coordinate is 1.1? The point is a point on the graph. The graph has the equation y equals x squared. if you know the input 1.1, then the y coordinate is computed using 1.1 squared, right? Yeah, 1.21, 1.21. So can I just use the form of 1.1 squared? So in this case, now for question 4, okay, for question 4, on the numerator we have 1.1 squared. So that's the y coordinate of the second point, okay, minus the y coordinate of the first point, so which is 1. On denominator, you have 1.1, the difference between two x coordinates, right? 1.1 minus 1, okay. If you compute this number, you are going to get the answer to question number 4, okay. But in most cases, anybody very quickly can tell me the answer to this? If I remember correctly, if I guess correctly, it's 2.1. Sure, thank you. Thank you. It's 2.1. Okay. So we're done question 4. Okay. Graphically, I believe you see. I'm trying to fix the first point, 1, 1. I'm trying to make the second point. The second point getting closer and closer to the first point. So that's the whole idea. Okay. Okay. You look at question 5. The first point is fixed. Okay. And the x coordinate of the second point is even closer to the first point than the case in question 4, of course, right? Now let's work on question 5. Okay. So the answer to question 5 is going to be something like the following. I still use m to denote the slope. Okay. And then the second point is even closer. It's 1.01, right? So the slope, I believe you can see the pattern now. Okay. On the numerator, you have the difference between two y coordinates, so which is 1.01 squared minus 1 squared. It doesn't matter 1 squared, you read square or not. Okay. But on denominator, you have 1.01 minus 1. Okay. This one should be 2.01. Okay. 2.01. And likewise for question number 6, I'm not going to write the details. I think you have seen the pattern already. I will write some details. It doesn't take me too much longer. Okay. I think you have seen the pattern. Okay. The y coordinate of the second point 1.001. I think that's the y coordinate of the second point is 1.001 squared minus 1 squared. On denominator, you have 1.001 minus 1. The slope of that secant line should be 2.001. Okay, so we're done question number 6. Again, now let's try to describe the points. The second point in particular, the first point is fixed. Okay, the first point is always 1, 1. The point with x coordinate of 1 and the y coordinate of 1. Okay, now let's try to observe the second point in question 3, 4, 5, 6. Okay, in question 3, 4, 5, 6, I'm trying to make the second point, in particular the x coordinate of the second point, or the second point, getting closer and closer to the first point. And we are trying to observe the slopes, the change of the slope of the secant line. Okay, now try to answer my question. Okay, I'm going to summarize a question. I'm going to organize a question. Now my question is, as the second point gets closer and closer to the first point 1, the slope of the second line gets closer and closer to what number? I'm going to repeat my question. Okay. As the second point on the curve, on the graph of the function gets closer and closer to the first point, the slope of the second line gets closer and closer to 2. I think many of you guys have answered my question. Okay. Thank you. So what is the meaning of 2? I'm looking for the meaning of this 2. Now I'm looking for the meaning of 2. Yeah, 2 is the limit. So what is the meaning of 2? So geometric meaning, in particular the geometric meaning. The geometric meaning of 2 is the limit. So what is the meaning of the limit? What is the meaning of 2? Okay, now let's... Okay. So this thing is pretty cool actually. I just found out decimals can do this. Okay. We start from h value of 1. Okay, you do not have to look at my left hand side. Okay, that's what we are doing. Okay, you look at the change of the second line. You look at the change of the second line, please. Okay, I'm trying to make the second point gets closer and closer to the first point. For each secant line, it's possible to compute the slope. I'm trying to make the second point gets closer and closer to the first point. By that we mean now we are trying to observe the limit location. So what is the limit location of the secant line? What is the limit location of the secant line? I'm just looking for a keyword. So what is the limit location of the secant line as the second point gets closer and closer to the first point? So I'm just looking for one term, for a name. Sorry, I messed up that thing. I think it's somewhere in here. I'm just looking for when the second point gets very close to the first point. I'm looking for the limit location of the secant line. Okay, it's tangent line. Okay, tangent line. So that makes sense. Tangent line is a line cutting the graph at only one point. It's not very rigorous, but intuitively in this case, it's kind of that. Okay, we call that a tangent line. So does that make sense? I'm trying to say as the second point gets closer and closer to the first point, as the second point approaches the first point, the limit location of the secant line is tangent line. Okay, it's tangent line. Originally, I was looking for the meaning of 2. So what is the meaning of 2? In question 3, you have the slope of the secant line 3, right? In question 4, you have the slope of the secant line 2.1. So what should be the slope of the tangent line? The slope of the tangent line is equal to 2. Okay. Now we are going to answer question 7. In question 7, use the above observations to guess the slope of the tangent line to the graph at the point where x equals 1. Again, the limit location of the secant line is the tangent line. Can I say that way? So the answer to question 7 is equal to 2. I know these numbers are getting closer and closer to 2, right? 3, 2.1, 2.01, 2.001. These numbers are getting closer and closer to 2. I was looking for the meaning of 2. Okay, 2 is the slope of the tangent line. So the answer to question 7 is nothing but Okay, just write one number. It's 2, right? In question 7, we just look for the slope. We just want to guess the slope of the tangent line. Very shortly, you are going to see this 2 is actually the derivative of the function at x value of 1. I will convince you very shortly. Okay. In question number 8, 9, and 10, we are going to talk about some general case. In particular, in question number 8, we are going to get the slope of the secant line to the graph passing through the point. One point has x coordinate of 1. The second point has x coordinate of 1 plus h. Okay. This slide is a little bit messy now. I'm going to work on questions 8 and 9 and 10 on a new slide. Okay. Okay, now let's work on question number 8 first. Again, the first point is fixed. The first point is the point with x coordinate of 1. And okay, I will go over the thing in some more details. Okay, we evaluate the function at 1. The function is the same function, f of x equals x squared. Okay, we evaluate the function at 1. So you have 1 squared, so which is 1. That gives you a point on the graph with x coordinate of 1 and y coordinate of 1, right? Now look at question 8. In question 8, the second point is 1 plus h. So temporarily you imagine h is a tiny positive number. H is a tiny positive number. When h value is 1, you'll have question 3. When h value is 0.1, you'll have question 4, right? When h value is 0.01, you'll have question 5, and so on. Okay. But this time we are going to talk about the general case. H can be any tiny positive number. Okay. By that we mean to get the point, you have to tell me the two numbers, x coordinate and y coordinate, right? To get the y coordinate, we evaluate the function at 1 plus h. In this case, it's 1 plus h, the whole thing squared. It's because the function is f of x is x squared, right? Alright. So the point on the graph has x coordinate of 1 plus h and the y coordinate of 1 plus h, the whole thing squared. Probably I do not need that form. The point can also be written in the following form. X coordinate is 1 plus h, and the y coordinate is the value of the function at 1 plus h. It's probably easier for my purpose to give the point that way. Okay. Now for question 8, we are trying to get the slope of the secant line. The slope of the secant line. For question 8, okay? For question 8, I'm going to use m to denote the slope of the secant line in question 8. The same thing is computed using the difference between two y coordinates on the numerator. Again, so that's the first point, the circle, okay? That is the second point. Now we are going to represent the slope of the line passing through the 2 points. Okay. So on the numerator, you have the value of the function at 1 plus h minus the value of the function at 1. It's actually the difference between two y coordinates. Okay. And on denominator, you have, anybody want to tell me the denominator? The difference between two x coordinates? It's 1 plus h minus 1. The difference between two circled x coordinates is h, right? The denominator is h, right? In question for question 8, I know it's possible to simplify the answer. Actually, for the point, I was trying to write x coordinate as 1. I was trying to write y coordinate as the value of the function at 1 to make the notations consistent. Okay. But for some purpose, I want to leave the answer like that for question 8. Any questions about this? Again, if h value is 1, you have question 3. If you have h value is 0.1, you have question 4, and so on. Okay.
Why is the denominator just h and not h squared?
The denominator is the difference between two x coordinates, right? It's 1 plus h. Now look at the mouse cursor. It's 1 plus h minus 1. The formula for computing the slope is, I think I told you the formula. It's y2 minus y1 over x2 minus x1. The denominator is the difference between two x coordinates. It's 1 plus h minus 1. So,
Okay, I see it now, thanks.
okay, sure. Okay, so that's question number 8. Okay, now you look at question 9. Okay, in question 9, we're actually officially computing the slope of the secant. Sorry. Now let me try again. Okay, for question 9, we're actually going to officially compute the slope of the tangent line. For question 8, can I change my notation to something different? I want to use. Can I use m bar for the slope of the secant line? For some purpose, I want to change my notations. Okay. Actually, the notation for question 3, I want to change to m bar. For question 4, I want to change to m bar for some purpose. Okay. As long as you know the meaning, the convention of my notation. M bar is for the slope of the secant lines. Okay. Okay. So because I want to use m to denote the slope of the tangent line now. Okay. Now for question 9, you guys are smart. You guys are smart. I'm looking for a relation between these two things. In question 9, I want to use m to denote the slope of the tangent line. I want to use m bar to denote the slope of the secant line. In question 8, now I'm looking for a relation between the two numbers, m and m bar. I want you to recall the tangent line is actually the limit location of the secant line. As the second point gets closer and closer to the first point. Now I'm looking for a relation between m and m bar. Probably it's easier for you to see if I show you this again. Okay, secant line gets closer and closer to the tangent line. Now you can observe h value in here. Okay, it's too small for you to see properly. So can you see the screen? The stuff in the brackets is actually the slope of the secant line connecting the second point and the first point. Okay. Now I'm going to make this h gets closer and closer to 0. This will make the second point gets closer and closer to the first point. The limit location is the tangent line. Okay. Now in question 9, I'm looking for a relation between these two things. M, the slope of the tangent line, and bar, the slope of the secant line. Yeah, m is the limit. That's good. Yeah, that's good. So m is the limit. M is the limit. If I'm looking for the full sentence, the limit it should be the limit as what approaches what. Okay. M should be the limit. I hope it makes sense. It's the limit of the slope of the secant line as h approaches what number? Now you look at the meaning of h. Or we can look at this screen. I was making h getting closer and closer to 0 as h goes to 0. So that makes sense? Yeah, in any case, I know it's kind of so time consuming, but the geometric meaning of the derivative is so important. I still want to mention this. I still want to do this. Okay. I'm running out of space on this slide. Now we are going to actually plug in the things to compute the slope. Actually, it's the thing we did last time. Okay. For question 9, I will give you one more. I will give you one more thing, and then we compute the limit. Okay. The limit is actually the limit as h goes to 0. M bar, you got the answer to M bar in question 8, right? The denominator is 8. Sorry. You look at the mouse cursor. M bar is here. I just copy M bar from question 8 to here. Okay. So this one is the value of the function at 1 plus h minus the value of the function at 1. Now I will move on to the next slide, okay, to compute the limit. Actually, we have seen the limit last time. Okay, now let's recall M. M is computed using the limit as h goes to 0. The denominator is h. The numerator is f of 1 plus h minus 1, right? So minus f of 1. I think you did many questions like that on the assignment already. Anybody want to tell me the meaning of this limit? This is the limit of a difference quotient. This limit is defined as the derivative, right? So we have seen that already. It's actually the derivative of the function at 1. The derivative of the function at 1, according to what I told you in last class, the limit of that difference quotient is the derivative of the function at 1, right? Now we're actually trying to compute that. I think we have seen the calculation many times already. I can go over that a little bit quicker. Okay. To compute the limit, I told you before, you have to copy the limit notation all the way until almost the last step. Okay. On the numerator, now let's recall the function. So this time is x squared. F of x equals x squared. Okay. The first term on the numerator is the value of the function at 1 plus h. So you have 1 plus h, the whole thing squared, right? And then the value of the function at 1. You plug 1 into the function, you have 1, right? 1 squared is 1, of course. We have seen this many times. You know how to expand 1 plus h, the whole thing squared. It's 1 squared, which is 1, and then plus. It's kind of, I'm trying to use the formula. I will remind you of the formula again. I mentioned that last time. Right. Okay, the second term is 2h, right? And then plus h squared minus 1. The 1 is cancelled that way. Again, factor before cancelling, as I told you last time. Factor the numerator, you take out a common factor of h, and then you have 2 plus h inside the brackets, right? So denominator is h. Now from numerator and denominator, you can cancel out h, right? The reason you can cancel it out, I want to mention that again, is when taking this limit the limit is determined by the values of the function at numbers very close to 0, but not equal to 0. When h is not equal to 0, it's permissible to cancel out h that way. Okay. Now 2 plus h is an elementary function. You plug each value of 0 into the function, you can have the limit. So the limit of the function is 2. Okay. By that we mean the derivative of the function at 1 is equal to 2. Actually, it's the, now look at the meaning, this lowercase m, that is the slope of the tangent line. So that makes sense. The derivative of the function at 1 is the slope of the tangent line to the graph of that function at the point when the x coordinate is 1, when x value is 1. Okay. Again, I told you the conclusion last time. I told you the geometric meaning of the derivative of the function at a point last time. So here I just try to show you why. You look at the screen. I showed you the screen last time, right? The geometric significance of the derivatives. F of a is the slope of the tangent line to the curve, to the graph of the function at the point when x coordinate is a. For the question we just mentioned, a value was 1, the function was x squared, right? Any questions about this? So this thing is so important actually. You're going to see why later. Now for instance, the tangent line, in particular the slope of the tangent line, is going to be useful for many purposes, including Newton's method and some numerical method, approximation. You're going to see those things later. Okay. I was trying to make some more comments, but I forgot what I was trying to say. Okay, we are not done the question yet. We still have question number 10. Okay. Now let's work on question 10. Question 10 is simple. For question 10, you just need the point slope form. In question 10, we are looking for the equation of the tangent line to the graph at the point where x equals 1. I will copy the question to the PowerPoint. Okay. Actually, on the last assignment, you did a few questions like this, right? But still, I'm going to make some more comments. Okay. In question 10, we are looking for the equation of the tangent line to the graph at the point where x value is 1. For this one, I'm going to do the question in some more details. And then I'm going to make some more comments. The function in this particular case is x squared. Is a problem, right? To get the equation of a line, we need two things. In this particular case, we need a point and we need the slope. You know the slope is 2, right? According to the calculation on the last slide. You know the slope is 2. So we are looking for a point. We need a point. Okay. So okay. Now let's get the point first, and then I'm going to review the formula for you. Okay. Now the solution to question 10. We'll get the point when x coordinate is 1 first. Okay. So by that we mean to get the point, you have to tell me x coordinate. We know x coordinate is 1. we're looking for y-coordinate. To get the y-coordinate, because the point is on the curve, on the graph, the y-coordinate is found by evaluating the function at 1. Okay. So the value of the function at 1 is 1 squared, so which is 1. We have seen this many times, right? So the point with x-coordinate of 1, y-coordinate of 1 is on the line, on the tangent line. Okay, now you look at, we are looking for the equation of that line, right? Tangent line. Actually, when h is very tiny. Okay. When h is kind of 0. From question 9, the slope, the derivative of the function at 1. I think I gave you the notation before. The derivative of the function at 1 is the slope. So we have seen that, right? Equals 2 gives the slope of the tangent line. I told you earlier, to get the equation of the line we need two things. In this particular case, we need the point slope form. We need a point. We need the coordinates of a point, okay, on the line. We need the slope, the derivative of the function at 1. This value 2 is a slope. Now I'm going to review the point slope form. I will run the review on top of the screen. Okay. If you know the slope is m, if you know a point with x coordinate of x naught and y, can I use AB instead? I think in high school you probably used AB. If you have the slope of m, if you have the point on the line with x coordinate of a and y coordinate of b. Again, if you have a point, if you have the slope, then we have the point slope form for the equation of the line. The point slope form is y minus y coordinate of the point equals the slope, right? X minus x coordinate of the point in brackets. This is called the point slope form. I'm running out of space, so probably you can make some comments here. This is called point slope form. Okay. In this particular case, the point is the point 1, 1. The slope is 2. Now you just replace AB and M with some particular numbers. M value is 2, right? AB values are 1 and 1. Okay. So in this case, the equation tangent line is y minus y coordinate of the point, which is 1, equals the slope, which is 2 times x minus x coordinate of the point in brackets, right? I know in high school you probably told to convert the equation of the line to some other forms, the standard form, the general form, whatever form. But for the purpose of this course, you just leave the answer like that. It's fine. I'm trying to say you do not have to simplify the equation to any other form. This form, the point slope form, I can see more information than any other form. For instance, if you write the equation in that form, I can see a point on the line 1, 1. I can see the slope of the line 2. Okay. I'm trying to say that's the final answer. Okay. To question 10. So we're done part 2. Again, the intention of part 2 is trying to convince you the geometric meaning of the derivative is the slope of a tangent line. The slope of the tangent line, in this particular case, passing through the point with x coordinate of 1. Okay. In this process, I also told you how to write the equation of the tangent line. Okay. Any questions about this? Any questions about this? I'll take that as a no. Okay. So don't be shy if you have any questions. That's why you're here. So that's why I'm here. I told you at the beginning of the class I would give you a chance to ask questions on your assignments. Now, anybody has any questions about 4 and 5? Question 4 and question 5? In part 6 on your assignment? I know your last assignment had a little too many questions, but you had a long break. Sorry. Anybody has any questions about 4 and 5? Or 3, 4, and 5? Last time I think I did question 1. I did question 2 for you, probably. Okay, if you don't have any questions, I'm going to go over a very similar question. It's probably we'll just go over question 4. Doesn't matter. If you did anything wrong, you have chance to resubmit the assignment by the end of the day. Okay, I will mark your new submission. But in any case, so before the due time, the due date, you have to submit your work, and then after the class you can resubmit your work. If you read the instructions, I think I meant those things. Anyway, I'm going to go over at least one question like that. Okay, I will go over question 4 on your assignment, the actual assignment question. We mentioned the definition of the derivative last time. I'm going to review that. Now look at the definitions here. So this is the definition of the derivative of the function at some number a. Okay. For the question, we're going to talk about a value. I believe a value is 3. A value is 3, right? We're trying to evaluate the derivative of the function at 3 using the definition. I know probably some of you guys know a little bit of calculus before, but for all these questions I want you to use the definition to evaluate the derivative. If I want you to use the definition, I mean to use that formula. That's the definition. The derivative is defined as the limit of a difference quotient. Okay, we'll use the definition to do that. That's assignment question. At least you have tried, or you got the answer already. So I will go over that a little bit quicker. Okay. For question 4a, I want you to copy the definition first, right? The derivative of the function 3 equals the derivative of the function at a number is defined as the limit of a difference quotient. Copy the definition first, replace a value with 3 in this particular case. I'm trying to say 3 plus h, right? F of 3 plus h, I mean the value of the function at 3. Again, we call the whole thing, people call the whole thing the limit of a difference quotient. Probably I need a bigger space. I'm going to plug in some numbers from here. Doesn't matter. We'll start a new line. In the first step, that's what I meant by copying the formula. Okay, copy the formula so that you have something to follow. And then for the particular function, you write the meaning of the two terms on the numerator. On the numerator, the first term is kind of the value of the function at 3 plus h. Wherever you see x in the function, you will replace x with 3 plus h. In this particular case, you have 3x, you see x, you replace x with 3 plus h. Okay. I kind of made a mistake on purpose. You treat 3 plus h as a whole. I'm trying to say the brackets are essential in here, right? You have to use brackets. The original function is square root of 3x. Square root of 3x. Wherever you see x, you replace x with 3 plus h. And then the next term is the value of the function at 3. I think you plug 3 into the function, you should have square root of 3. 3 times 3, you have square root of 9, so which is 3. I think we can just write 3 in here. Okay. The denominator is nothing but h. Okay. Now we need to rationalize the numerator. I told you the trick last time, right? I think in high school, I have seen many people writing, rationalizing the numerator the following way. You kind of multiply the whole thing by 1, and then you multiply the numerator and the denominator by the conjugate of the whole thing in here. I told you the meaning of conjugate last time, right? So you just replace the sign, replace the minus sign with plus sign. You have the conjugate. So do you see, you essentially multiply the whole thing by 1. You look at the mouse cursor. That term is essentially 1. So the two functions are the same. Right? You have to copy the limit notation in this step. Now we multiply the two factors on the numerator. Okay, you have the form of a minus b times a plus b. You do need to use the formula something like this: a minus b times a plus b equals a squared minus b squared. Of course, you can FOIL, but it's much easier if you just use that formula. Actually, why we can get rid of the radical on the numerator by doing this, the reason is that formula, right? Now let's see what's going on next. Okay. On the numerator, you have the form of a minus b times a plus b. So you're going to have a squared minus b squared. So your a squared in this particular case is going to be 3 times 3 plus h. The square root is gone. That's your a squared. Okay. And then minus b squared, your b squared in this particular case is actually 9. So that makes sense. 3 is your value of b. 3 squared is 9. probably that's a question you did on the assignment. I'm running too slow. But on denominator, you have h times square root of 3 times 3 plus h. And then plus 3. You just copy the denominator. For denominator, do not multiply them out. In many cases, we like the factor form better because we want to cancel something out. Okay. I think I'm running out of space already. Okay, I will see if I can squeeze everything on the same slide. But now you look at the numerator now. You look at the numerator. The numerator you multiply this out. You have 9 plus 3h, right? Minus 9. 9 is cancelled, right? On denominator you have h times the whole thing in the brackets. Okay, it doesn't matter. 3 times. I'm just copying the stuff inside the brackets on denominator. Again, 9 and 9 is cancelled out, and then you cancel out h from the numerator and denominator. After canceling out h, you plug h value of 0 into the function. Okay, you plug h value of 0 into the function. I do not know the final answer, but I think the numerator 3, if you replace h with 0 on denominator, you have square root of 9. Square root of 9 is 3, and then plus this 3, you have 6, right? So do you have 1/2? Can anybody confirm you have the same answer as me? I just want to make sure I did not mess anything up. Okay, thank you. Okay, so that's how we get the answer to question A. Now we just, actually I told you the geometric meaning last time. So this number has a meaning, right? This 1/2 has a meaning. Now you'll know it better. 1/2 is actually the slope of the tangent line to the graph of that function. You look at the mouse cursor, f of x. When x value is 3. Okay. Now we are ready to do question B. In question B, we need to do a little bit more work. Okay, we got the slope of the tangent line in question A. In question B, you do not have to redo the whole thing. You just use the answer to question A. That is the slope. In question B, we need a point. We have x coordinate of the point. We need the y coordinate of the point. Okay. I will copy the question to the next slide. Let me show you what I mean. Okay. Now we'll do question B. In question B, we need the point, right? You're just given x coordinate of the point. You have to evaluate the given function at 3. So which is square root of 3 times 3. So which is 3. I think it's 3, right? The value of the function at 3 is equal to 3. So the point with x coordinate of 3 and the y coordinate of 3 is on the line. It's on the tangent line. For question 1, we have seen 1/2 is the slope of the line, right? So maybe from question A, I mean, okay. From question A, the derivative of the function at 3, which is 1/2, gives the slope of the tangent line. So its equation, the equation of the tangent line is the following. Using the point slope form, it's y minus y coordinate of the point equals the slope, so which is 1/2, right, times x minus x coordinate of the point. That's the complete solution to question B. Okay. Now let's work on the question first. Very shortly, I'm going to tell me what I'm trying to motivate. Okay. At this point, the only way we can do it is to use the definition, the limit of a difference quotient. Okay. We'll do that first. At this point, you imagine A is any real number. A is any real number. A could be 1, A could be 5, A could be 10, A could be any fixed number. Okay. In any case, we copy the definition first. The derivative of the function at any number A is the limit of a difference quotient. The limit as h goes to 0. Denominator is always h. The top you have a difference quotient. Copy the formula first. Okay. On the numerator you have the value of the function at a plus h. In this case, we are trying to evaluate the derivative at a, right? On numerator you have f of a plus h, the value of the function at a plus h, minus the value of the function at a. Okay. And then we replace the numerator with something for the particular function. Okay. H goes to 0. Denominator is h. The value of the function at a plus h. Again, wherever you see a plus h, you replace. Wherever you see x in the original function, you replace x with a plus h. Probably you want to use brackets. Okay. I'm trying to say the value of the function at a plus h. You have a plus h, the whole thing squared, the whole thing cubed. The whole thing cubed minus the value of the function at a is of course a cubed. The function is x cubed. Okay. Simple enough. And then the limit as h goes to 0. The denominator is h. You learned the following formula in high school. I will help you to recall the formula. It's the formula for expanding a plus h. In general, a plus b, the whole thing cubed. Anybody can remember the formula? It's kind of a cubed and then plus 3a squared b, and then plus 3ab squared. Altogether there should be 4 terms, right? And then plus b cubed. I'm pretty sure you learned that formula in high school. Okay. If you do not remember it, try to memorize right now. Okay. By that we mean we can use the formula. We can use that formula to expand a plus h, the whole thing cubed. Or alternatively, you just FOIL a plus h, the whole thing cubed. You multiply a plus h 3 times, but it's much easier if you use that formula. Okay. I'm trying to say the numerator now becomes a cubed, and then plus 3a squared h, and then plus 3a h squared, and then plus h cubed minus a cubed. Okay. And then it's kind of the same idea we have seen before. a cubed and a cubed are cancelled out. Okay. And then remember, for the numerator, factor before cancelling. Factor before cancelling. Okay. Factor the numerator. After canceling out a squared, you have three terms. Every term has a factor of h. You kind of take out h, right? You take out h from all the three terms. You have 3a squared and then plus 3a h and then plus h squared after taking out h, right? I want to repeat, factor before cancelling. So just remember that there's a common mistake in here. Actually, at this point you can cancel out h from the numerator and the denominator, and then plug h value of 0 into the function. The final answer should be 3a squared. Simple, right? It's actually very comparable to evaluating the derivative of x squared at number 1. It's very similar. Okay. But now, using this question, I'm going to motivate a new concept. Okay. After you know the answer to that, in the question on top, I was looking for the derivative of the function at a. I was looking for the derivative of the function at 1. I was looking for the derivative of the function at 5. So do we need to redo these two questions? The derivative of the function at 1 and the derivative of the function at 5? Actually, for the calculation we just did, according to the calculation we just did, a can be any number. Anybody want to use the answer to the question we just did to tell me the derivative of the function at 1? So please try to answer my question. Please. Anybody want to use the answer to the derivative of the function at a to tell me the answer? The derivative of yeah, that's 3. You just replace a value with 1, so you have 3, right? And then the derivative of the function at 5. The derivative of the function at 5, it could be a little ugly. 5 times 5 is 25. I think it's 50. Is that right? Yeah, 3 times. Yeah, 75 is right. You're right. It's 75. 3 times 5 squared. 75. Okay, now I'm going to. Now you listen to me carefully. I'm going to motivate a new concept. Okay. Now my point is this a value can be any number. My point is we can treat the derivative of the function at a equals 3a squared as a function. Now let's recall the definition of a function. The definition of a function is a function can process inputs, right, and producing outputs. There's only one condition. Every input has one and only one output. That's the definition of a function. Okay. Actually, now we can treat a as a variable. By that we mean a can be 1, a can be 5, a can be any number, right? As long as I give you the input. Now let's say I give you the input of 1. Using that rule, using 3a squared, you can get me the answer of 3, right? It means the derivative of the function at 1 is equal to 3. The derivative of the function at 5 is equal to 75. Actually, we can get the derivative of the function at any number. I'm trying to say for each input a, we can have the output. By that we mean we can treat the derivative as a function. You have an input A. If you give me an input A, I can give you the output. But the commonly used notation for the variable is not A. In this case, we treat A as a variable. I said that, right? But the commonly used notation is not A. A commonly used notation of a variable in calculus, in pre-calculus, in any course is actually X, right? I'm motivating a new concept, the derivative as a function. I will replace A with X to mean X is a variable, to mean A is a variable. Do you know what I mean? Wherever you see A, I replace A with X. I replace A with X. I replace A with X. All the way, okay? That's how we get the derivative as a function. Actually, the new definition is nothing but that. It's something not too new, slightly new. We just treat X as a variable. Okay. I will show you the definition on the course manual. Okay. The derivative as a function. It's here. It's here. Okay. It's actually a new section. The derivative as a function is defined as that. So later on, I'm going to do a few more questions to show you the meaning. When I do some more questions, I will make more comments. Okay, how to use that formula. Essentially, we have seen the formula already, right? We just treated the derivative as a function. Okay. Actually, according to this question, there's something I want you to memorize. So later on, we are going to generalize that. The derivative of x cubed is equal to 3x. If you learned some calculus before, you know it's actually 3x squared. That's actually a particular case of the power rule. At this point, I want you to kind of memorize that. Okay. So later on, we are going to generalize this. Okay. But before that, we are going to do more questions. Okay. When I do more questions, I'm going to make some more comments. Okay, we'll do whichever you want to do first. We'll do question number 7 first. Okay. In addition to question 7, probably I'm going to ask you to evaluate a few more things. Evaluate the derivative of the function at 1, maybe the derivative of the function at 4, the derivative of the function at 9. I'm trying to use some nicer numbers in terms of square roots. In any case, we'll do 7 first. Okay. For this one, we use definition. We copy definition first. Okay. The derivative of a function as a function, the formula is the following. I'm trying to say, at this location, at this spot, if you do not see any particular number, you need to use the formula, and we are looking for the derivative as a function. Okay. By that we mean x can be any number in the domain. X can be any non-negative number, actually positive number in this particular case. We take the limit as h goes to 0, copy the formula. The formula is always the same. The value of the function at x plus h. It's not too rigorous to say that way, but I'm trying to tell you the meaning. and then f of x, okay. Now remember one thing, okay? I told you I'm going to make some comments when we do questions. When evaluating the limit, you treat x as a constant, like what we did earlier. When evaluating the limit, you treat x as a constant. But after getting the answer, after getting the final answer, you treat x as a variable. I hope it's not too confusing. After getting the answer, x value, or originally a value, it can be 1, can be 2, can be 5, right? But when you compute that limit, you treat x as a constant. When computing the limit, you treat h as a variable. You treat x as a number. After getting the answer, you treat x as a variable. X can be 1, can be 5, can be any number, right? The same idea in here, okay? Before we compute the limit, we have to replace the numerator for the particular function first, okay? So the value of the function at x plus h, again treat x as a constant, okay? If you're too confused, you imagine x is a, is a number a positive number a in this particular case, and then you replace a with x. Simple enough. The value of the function at x plus h, it should be square root of x plus h. Wherever you see x in here, to compute the circled term, wherever you see x, you replace x with x plus h. In some cases, try to use brackets to avoid mistakes, but in this case, it's not necessary. Okay. The second term is kind of the value of the function at x. Of course, it's a square root of x. Again, if you feel confused, you just replace x with a so that you know what's going on. Okay. The denominator is h. The same trick as we mentioned before. Okay. You multiply the whole thing by 1. So which is the conjugate, which is the quotient of the same conjugate of this numerator. We have seen the same trick many times, I think. The technique we use is the same thing. We want to get rid of the radical on the numerator. We call it rationalizing the numerator, right? If it's real face-to-face class, I would ask people to try this. I will check your work. I could walk around and check your work, but now I can't. Now the denominator is h times, I just copied the denominator from here. And then the numerator, you use the same formula. You have the form of a minus b times a plus b, right? And then a minus b times a plus b is a squared minus b squared. In this case, your a squared is x plus h. Your b squared is x, right? The same as before, x and x is cancelled. And then after cancelling out x, h and h is cancelled. The numerator is going to be 1. After cancelling out x and h, you can plug h value of 0 into the function. Okay. Again, when computing this limit, you treat x as a constant. You imagine x as a, okay. But after getting the answer, you treat x as a variable. Okay, you plug h value of 0 into the function. On denominator, you have 2 of square root of x, right? So the final answer is kind of 1 over 2 square root of x. Sorry, square root of x. Okay. I want to repeat. I mentioned earlier. When evaluating the limit, when computing that limit, you treat x as a constant. You treat h as the variable. But after getting the answer, you can treat x as a variable. By that we mean after. Now let's try to use the answer to get the derivative of the function at 1. You want to tell me the derivative of square root of x at 1 using the answer? Okay, I will answer your question first, Alia. Okay, for this one, I'm going to run a little bit slower. The numerator is 1, right? The numerator is 1. Now to evaluate the limit, we plug h value of 0 into the denominator. Okay. On denominator, you have square root of x, and then plus square root of x, right? You have 2 square root of x. You combine these two terms, you have 1 over 2 square root of x. So did I answer your question? Okay, thank you. Cool. Okay, so we have this, right? Again, after getting the answer, we can treat x as a variable. X can be 1, x can be 4, x can be 9, x can be actually any real number. Can be 10, can be 1.1, can be e, can be pi, okay? Can be any number, okay? Using the answer we just computed, anybody want to tell me the derivative of the function at 1, for instance? You just replace x, yeah, it's 1/2, right? That's what I meant by after getting the answer, you can treat the x as a variable. So the whole thing, the derivative of the function is equal to 1 over 2 square root of x. The whole thing is a function now, okay? Because we have a variable, okay? And likewise, the derivative of the function at 4 is equal to, I don't know, it's 1 over 4. Is that right? You plug 4 into that function. It's 1. So thank you for confirming that for me. Still, we need one more. The derivative of the function at 9, I believe it's 1 over 6. I'm trying to say, using the derivative as a function, it covers many particular cases, right? That's why I said, after getting the answer, you can treat x as a variable. Okay. Actually, at this point, there's a famous formula I want you to memorize. It's also a particular case of the power rule we are going to talk about later. You're probably in next class. But that's a formula because you are going to see to differentiate square root of x over and over again. And by the way, differentiating is taking the derivative, the same thing. Okay. Sometimes I just say differentiate square root of x. You get 1 over 2 square root of x. Okay. That's another formula I want you to memorize. Okay. Okay. Another famous formula you need to memorize. Okay. Any questions about this? If you don't have any questions, we'll talk about one other famous formula. Okay. We'll move on to question 5. I think you got the idea already. In most cases, at this point, people tend to be able to do things on their own. Actually, I graded your last assignment. So do not miss the notations. Now, for instance, the limit notation, you have to write the limit as what approaches what. So do not just write the limit. So I'm trying to say, if you just write, now for instance, in this case, if you just write the limit, so this does not make any sense. You have to tell me the limit as h goes to 0. Okay. I'm trying to say use complete notations. I know probably in past too many years you did too many multiple choice, fill in blank questions and so on, but I rarely use those questions. I'm trying to say use proper notations. Okay. If you just have multiple choice, fill in blanks and so on, you may not care too much about the notations. But I'm looking for proper notations, please. Okay. The same as before. Also, we're trying to evaluate the derivative at a few particular numbers. So maybe at 2, at whatever number 3. Okay. I mean the derivative of the function at 2 or 3. Now remember where to use prime notation, where not to use prime notation. So with the prime notation, it means the derivative of the function. Okay. So don't think I'm nagging now. I do get old. I start to nag a lot, but I'm trying to recall many common mistakes in my mind now. Okay. In any case, we evaluate the derivative as a function first. Okay. The derivative of the function is defined as the limit of a difference quotient. Copy the definition. And by the way, I haven't fully decided. Your midterm and the final, everything could be closed book. There's no formula sheet. You need to memorize everything. It's always the requirement of the course. So trust me, eventually you're going to like it. I'm trying to say memorize the formula. Okay. It's kind of the value of the function at x plus h. You have wherever you see x in the original function, to get the first term on the numerator, you replace x with x plus h. F of x is of course 1 over x. Okay. Do I still need to repeat that? When evaluating the limit, treat x as a constant. Okay. Treat h as a variable. We take the limit with respect to h. To compare the numerator, we need a common denominator, right? The common denominator is x times x plus h. Can I jump a little bit? Rewrite the two fractions to two new fractions with a common denominator of x times x plus h. And then you subtract two fractions. Keep the common denominator and you subtract two numerators. I think the numerator is kind of x minus x plus h. I made a mistake on purpose. That's actually a common mistake. You need to use brackets here. If you want, I can add one more step. I'm going to add one more step. Probably it's easier for you guys to follow. I will add one more step in here, okay? the first fraction is converted to a new fraction with the common denominator of x times x plus h, right? By that we mean you multiply the numerator. Now look at the mouse cursor. You multiply the numerator and the denominator by x, and then to convert the second fraction to a new fraction with the common denominator, you multiply the numerator and the denominator by x plus h. Now I believe it's easier to follow now, right? The way I wrote this line is a little weird, but we are almost ready to get the final answer. Okay. Still want to include everything on one slide. From the numerator, you cancel out x. I think on numerator you have negative h in here, right? And then x times x plus h. On denominator you have h. So be careful. A common mistake is so I'm trying to say. So here you have negative h. It's a common mistake, missing the negative sign. At this point, it's permissible. We mentioned before, it's permissible to cancel out h like that, right? You have 1 on numerator. You have 1 in here. The final answer. I think we are ready to get the final answer. To get the final answer, you plug h value of 0 into the function, right? We can do that because we treat x as a constant, so the numerator is an elementary function. To get the limit, you plug h value of 0 into the function. After plugging in h value of 0, the limit notation is gone. And then the answer to the limit is a number. If we treat x as a constant, the answer to the limit is a number. Okay, the final answer, you replace h with 0, x times x. We combine x times x to x squared. I think the final answer is going to be negative 1 over x squared. Any questions about that? So here comes another formula I want you to memorize. Okay. Here comes another formula I want you to memorize. The derivative of 1 over x is equal to negative 1 over x squared. That's another commonly used formula. Again, it's a particular case of the power rule. I'm going to make more comments in next class, but that's a commonly you'd better memorize that. Okay, that's a commonly used formula. Using the answer, again, when computing the limit, you treat x as a constant. We take the limit with respect to h, but after getting the answer, we treat x as a variable. Okay. Now let's use that idea to get the answer to the derivative of the function at 2. The derivative of the function at 2. I think you have negative 1/4, is that right? The derivative of the function at 3, you have negative 1 over 9. Okay, thank you. Cool. That's how this thing is useful. Okay, so probably using the answer to that question, to the question on the screen. I think that's one of the questions on the handout as well. Anybody try to generalize? Anybody want to try to generalize? How do we compute the derivative of x to the power of n? So just try to generalize. Yeah, probably I should give you one more question before it's easier for you to generalize. But I believe even from that question you can guess the derivative of the function x to the power of n, the power function. N times, yeah, it's kind of 3x squared, but I'm looking for the general formula. The derivative of x to the power of n is n times x to the power of n. Yeah, that's right. N minus 1 in here. Okay. And that's actually the famous power rule. Okay.